Hi everybody. We are going to deviate from our current project for a minute to do one of these random videos. I get a lot of questions, and I just got some more regarding how to use a signal generator. I'll make it kind of basic. How to use a signal generator when servicing a radio. Now, on the surface that sounds kind of strange, but hear me out here. Many of you do not have an actual RF radio signal generator, but you do have something similar to what you see in front of you here. This is a modern, very new style of signal generator, and this is an old one. And what these are usually referred to as is a function generator. Why is it called a function generator? Let me stop this. The reason these are called function generators is because they actually can output different mathematical function waveforms. So for instance, a sinusoidal waveform, a square waveform, a ramp, pulse, you can see all that. And some of them can even do what's called an arbitrary waveform, which is basically any waveform you can think of to make up. Now, I want to explain a couple things about how these work and why there are some challenges using these to work on radios. Then we're going to look at just a very basic rundown how to use one of these to work on a radio when you don't have an actual signal generator for radio. Now, first of all, let's take a quick look at a couple of examples of RF signal generators. Now here is, of course, a familiar face to many of you who have been watching my channel for some time. This is my HP8657 signal generator. And this really is a signal generator that is very well geared towards working with radio and RF. The problem is they can be very expensive. They are available on the used market, but you don't always know if the one you buy is properly aligned, if there's any problems with it. You don't know, if it even works. So you have some challenges, and if you're new to this hobby, it's not something you're going to want to take on. If you're experienced and you work with this stuff all the time, of course, But the other thing is this is very heavy, and it's very large. This goes way back to the back of the bench. I mean, it's very long and very heavy and big. And it only does one function, and that is it produces a sine wave, and very accurately, may I say, and it has very accurate amplitude on the output. And there's only two different things you can do. You can have just the straight sine wave, which is called a carrier wave. We'll talk about that in a minute. And you can do two different types of modulation. You can simulate an AM radio station or an FM radio station. We refer that to modulation. We'll talk about modulation in a minute as well. But this is really the best thing to have if you're just going to work on radio, as per se, like you're going to work on old tube table radios or transistor radios or even stereos. Even though this will not by itself generate a stereo signal, it will generate all the other signals that you need. So if you work on receivers, it's a good piece of equipment. Over here's another example. This is a Fluke 6071A, and it's the same thing as what you were looking at with the HP. It has a little different user interface, as you can see, and it does have a few more bells and whistles on it, but generally it is the same thing. It'll produce a carrier signal, and it will produce AM or FM modulation. And that's mainly what it's designed for. And it even tells you it's for radio frequency. That's what RF stands for. Beyond that, you can get into these very specialized signal generators, and I have several of them. This is my favorite. This is the SG80 Sendcore, And it is designed specifically for working on AM/FM stereo receivers. And it does one thing, and it does it very well. But once again, these are extremely hard to find and very expensive. And again, they do one thing and one thing only, so they're not very versatile if it's going to be the only thing you're going to have on your bench. Now, of course, you have the old vacuum tube signal generators, and you've seen a lot of those, like the ICO 324 and the Heathkit SG8 and many other very popular signal generators. And they're very good at just the sine wave and the AM modulation. And some of them had FM modulation. I'll show you a couple pictures of that up on the screen, because I don't want to go dig mine out. I don't really use them very much. But most of you are going to have this. And these are very versatile, but for one big reason, they are difficult to use when working on radios. Alright, I'm going to focus on this particular model, and it is similar to a lot of the modern arbitrary or function wave generators or signal generators that they have today. So this is a Rigol DG4162. Now, Siglent, GW Instech, OON, HP, Tektronix, or what's HP's name now? I forget. They keep changing it. Keysight. All of them have a similar model to this. They may be in a different case. This one has a thin case. Some of them have the short, long cases, that are shorter but longer. Not as tall but longer back, deeper, whatever you want to say. Doesn't matter. They all do the same thing in a very similar way. Some of them will have buttons like this one. Some of them will have less buttons, and you'll have menus that you have to go through in order to get to the same thing that we're going to do by hitting a button on this one. But the point that I'm making is they're all basically the same with a little bit different user interface. Now, there's so much one of these can do, and I'm going to keep this focused to those who want to use this to troubleshoot or to generate a signal for their radio. So you're going to do an AM or an FM radio or a receiver, and you just want to generate a radio signal to do your tests. That's what we're going to focus on. That's all this video is going to be. Now, the question that I received was, what is modulation? What is AM and FM? Why are they using some of the frequencies that they're using? This is very basic stuff, so I'm going to try to quickly, in a nutshell, go over that. The first thing you need to understand is, if you're going to work with radio, you're always going to leave this set to sine wave. Okay, see where it says sine wave? These are the different kind of waveforms. Let's look at them up on the scope here for a minute. Okay, we have an oscilloscope connected up to this, and before we go up and look at it, this is called a two-channel signal generator, and really all that means is there are two, just think of this as two signal generators in one case. So you have the yellow section, which is channel 1, and the blue section, which is channel 2, and they're both independent of one another, and I can generate two different signals at the same time. So for what we're doing, we only need to really worry about one, because we only need one signal. Okay? So whatever I'm doing on this channel, I can do the same on this channel and output it from this connector. Now, if we select sine wave, that's what you're going to choose if you're going to create a carrier signal for your radio. The first thing you have to look at with your particular signal generator is this tiny little wording right here. Let's look at it. See what that says? 160 megahertz. What does that mean? That means the highest frequency this can generate is 160 megahertz, or 160 million cycles per second. Okay? Now, Your AM radio uses radio frequencies that start at about 550 kilohertz or so and goes up somewhere around just below 1700 kilohertz or 1.7 megahertz. So 1.7 megahertz being the highest frequency with AM radio, this goes up to 160. This will be just fine for working on AM radio. Now when you look at an FM radio, FM broadcast starts at around 88 megahertz, or about 87.5, something like that, okay? Megahertz. And it tops out at 108 megahertz. So in order to get the entire frequency band, generate any frequency within an FM radio's capabilities, you have to have a signal generator that can output up to 108 megahertz. Since this one will go up to 160 megahertz, you're good. Now that's one of the trade-offs. Most function generators and arbitrary waveform generators, especially the less expensive ones, do not go this high. Many of them will only go up to 10 megahertz or 20 megahertz or something like that. They will not go this high. And that's one of the reasons that they cost less money. So you can get one that looks very similar to this, does everything that this does, but it will not go up into the frequencies you need to be to do FM radio. So that's one thing you have to remember. So this one can do it, so we're going to go ahead. Now the RF signal generators that are purpose-built for that, they all can go well within that range that you need. So that's another difference. So if I turn this sine wave on and I hit output, let's say we want to generate an AM radio signal at, let's say, 600 kilohertz. So I'll go to frequency and I'll type in 600 and see this comes up here, and I'll hit kilohertz. Okay, and amplitude is the height of that signal. Let's say we want that to be 500 millivolts. 500 millivolts RMS. Okay, and then we'll go ahead and we'll look at the scope and let's see what we have. Okay. And you can see all we have is a really nice sine wave, and it's operating at 600 kilohertz. Okay, it's actually a little, this thing's reading a little bit high. And part of that could be the scope itself. It depends on how many pulses you have in here. Sometimes when it samples it, it'll read it off a tiny little bit. Okay, so down here it says it's right on 600, and you can see up here it's averaging it a little different. But right here is the actual real-time frequency that it's measuring. See, it's right on 600. Now, let me move the scale down a little bit so it fits in the screen better. And so I shrunk it down a little bit, and if you look, we do the counting on this, we move the position up and down. Let's just get this centered in here. You can see we have about 1, 2, 3 gradicules. We are set to 500 millivolts per division, so there's 1500 millivolts there. And what do we have it set to? 500. So why is it 3 times what it should be? Anybody? Well, we get into that in some other videos. If you look at my video on connecting a 50 ohm terminated device to a non-50 ohm, a 50 ohm terminated test equipment to a non-50 ohm device, I get into some of this stuff. Remember, this is reading the peak value, not the RMS, which is what we selected, and this is not terminated properly with respect to the signal generator. So that's more than we need to get into in this video. But that is what we call a carrier signal right there. It's 600 kilohertz, and if I hooked an antenna up to this wire right here and transmitted it out, the radio would be able to pick that up when you tuned it into 600 kilohertz. Let's do that. Okay, I have a radio here. It's just a little Panasonic, and you can hear there's static on it right now. Hear the static? And I just have a couple of turns of wire here, just some random turns, connected to, a lead with a BNC plug on the end of it. And I have this set to the 600 kilohertz at 500 millivolts output. And I have this tuned to 600 kilohertz. Now watch what happens when I plug this in. I'm going to hold this close to the radio, and I'm going to plug this in. What happened? All the static went away, didn't it? The reason the static went away is because it is picking up this signal, and if I move it away, hear the static come back, I move it closer to it, it goes away. So let me get the microphone. Okay, here we go. Okay, so that is called an unmodulated carrier. All it is that sine wave, and the radio's tuning into it. So that explains what your carrier is. The next thing we want to learn about is what is modulation. Okay, so if you look on this particular piece of test equipment, there's a little button on here called mod. Mod stands for modulation. Now, some signal generators will have this in a menu, like on a soft key that you go, but they have modulation. So if we push this button, and you look over here, see where it says type? So right here we can hit type. Okay? If I hit the type button, there's all different kinds of modulation, and we're only going to worry about two kinds today, AM and FM. So let's select AM. Alright. Source, what that means is we can use an internal secondary signal generator called a modulation generator that's built into this signal generator, or you can connect to a connector on your signal generator that's usually on the rear of the unit somewhere. You see where it says mod? Come on and focus. See where it says that? Mod. That's your modulation input for channel 1 and for channel 2. And we're going to use the built-in. That's what we'll do most of the time. Okay? Internal modulation frequency. Now when you see them talk about 400 hertz modulated or 1 kilohertz modulated, they're talking about what frequency they want that secondary frequency generator to operate at. We're going to do something different today. We're going to go AM frequency, and we're going to set it to 1 hertz. Why are we going to do that? Well, I'll show you. And we're going to set it to 30%, and that's the depth. Now with that, let's talk about AM first of all. Let's go back up to the scope. Now if you remember, this is our carrier signal, and I have that mod turned off. Let's turn on that mod and see what it does to the signal. You see what it's doing? It kind of making it look like it's breathing. It's actually making the amplitude of that signal go up and down. Okay? The frequency is never changing, if you notice. It's still a 600 kilohertz signal on top of it that's carrying it, but you're just changing the amplitude or the power or the volume of that signal. You're modulating the amplitude. To modulate is to change something back and forth, right? And we're doing it at 1 hertz. So once every second, we're increasing and decreasing the amplitude 30%. So that's a 30% modulation. Now, if I change that percent, or the depth, to, let's say, 80%, see what's happening? Now it modulates it even further. And if I go to 100%, it's increasing it 100% and then dropping it back down. Okay? Now what would happen, let's go back down to 30%. What would happen if I make that modulation frequency go faster? Let's say we make it go 60 hertz. Okay? Or 500 hertz. Okay? It's moving so fast that it's making it look like there's two waveforms, but there really isn't. And if I slow the scope down, and I change my trigger, look what's happening. It's having a hard time locking on that right now, isn't it? But you can see that waveform, that is your 500 hertz riding on all those little tiny pulses that are in there, right? The really fast ones, the 600 kilohertz. So this is called an AM modulated signal, or an AM modulated carrier. All right? I could play with the settings on the scope with the trigger and I could make it sit still, but I'm not going to mess with it right now. Suffice it to say that that's it's not really doing that, it's the scope that's doing that where it's triggering. So does that make sense so far? That's AM modulation. So when a service manual tells you to set something to 600 kilohertz modulated at 500 hertz, or normally they use 400 hertz or 1 kilohertz. Those are just the standards that they use, because those are audible tones that you can hear with your ears. And really all a radio's job is to take that modulation, strip it off of that carrier, and put it through an amplifier so your ear can hear it. That's really what a radio does. A radio, first of all, tunes into that carrier, which is the 600 kilohertz. Then it detects that sound that's riding on that 600 kilohertz, takes away the 600 kilohertz, and only leaves behind the sound that you hear with your ears, and then amplifies it so your speaker can make it loud enough so you can hear it. That's really what this is all about. Now, FM isn't that much different. Let's go back to our 1 hertz. And let's go to FM modulation. Okay? All right. Okay. So if I take this and I go to 1 hertz, let's see, frequency 1 hertz. Okay. Now what we're doing is we have a again, a 600 kilohertz. See, it's 600 kilohertz carrier. And we look at the modulation, it's FM. We're using the internal modulation generator. We're modulating it at 1 hertz. So we're changing the frequency 1 time per second. And then the FM deviation is how many hertz you want to modulate it. In this case, we're modulating it 100 kilohertz. So it's going to go all the way up from, it'll go all the way from 600 kilohertz, it'll go to 650 and to 550, so it'll expand up and down. You should be able to see that now. Watch. And there it is. Okay. That's called your deviation. Alright. Okay, I stopped the waveform, and by the way, I did misspeak on that, the way this signal generator works. The deviation is how much it goes from the center frequency in each direction. There's different ways you can set that on other signal generators. This one's a little more simple. So if I measure from here to here, at where I stop the waveform, you can see that it's 502 kilohertz. So remember, we had a 600 kilohertz carrier. Well, when it's at the edge of its modulation, it's at 500 kilohertz. Okay, I didn't stop it right at the transition point when it goes by. And then it'll also go up to 700 kilohertz. So if I go, oh, let me do it again. And if we measure this one, I don't think I stopped it all the way in the right place, but we'll see. Oh, come on. There we go. And you could see 628 kilohertz, so it needs to shrink down a little more, but it would, or open up, or go up a little bit more, but it'll go up to 700. So it'll go from 500 to 700. It deviates 100 kilohertz in either direction. Okay? Hope that makes sense. So that's what FM, in other words, it's modulating the frequency. But if you notice, when this is running, if I turn the cursor off, notice that the amplitude never changes, only the frequency. Okay? So that's FM modulation. Now, FM is a little more difficult to work with when you're working with radio than AM, because there's some things that are going on that aren't going on in an AM radio. So I'm not going to get into all that today. The question I had was, I have a function generator, can I use it to work on my radio? And the answer is maybe. As long as your function generator can do modulation, and as long as the frequency limit of that, of the signal generator is high enough. So this one in particular can do it. Now there is one big caveat to all of this, and that is, look at the voltage output, the amplitude that's coming out of this port. It's 500 millivolts. And while that was okay to drive this coil for the radio, it was not okay for direct connecting it to your radio. Does that make sense? A radio signal is very tiny. It can be in the microvolts. And a microvolt is a millionth of 1 volt. Okay? This is a half of a volt. So, big difference. And here's the problem. If I go down to amplitude and I reduce this down as far as I can, 0.7 millivolts is the lowest that I can go, which is way too much, because That's 700 microvolts. And even at that level, you're right at the edge of what this thing can do, so the accuracy is not going to be perfect. So most waveform generators like this, these function generators, are not designed to generate a radio amplitude signal. They make a lot, the output is too high. So in other words, for that to work, you have to be able to attenuate this even smaller. I now have the signal generator properly terminated, and I have the scope properly terminated. Everything's set to 50 ohms. And you can see I have a 50 millivolt RMS signal, and it matches the 50 millivolt RMS that we have selected on the signal generator. Again, I did other videos on this, so I'm not repeating it. But as I said, millivolts is way too high. We need to get way down from there if we want to be able to work with radio, especially the front end of the radio. Like if we want to inject something in the RF stage or at the very early stage of the IF, it can be too much. So what we're going to use in this case are these little devices down here. Let me get the camera set so it doesn't go falling on me. Are these little things. These are called attenuators. So for instance, here's a 6 dB or 6 decibel attenuator. Now you can go online and you can do, they have little calculators that will convert your voltage to decibels, like dBV or dBm, which is milliamps. So we'll get in, dBs is another video. But this is a 6 dB attenuator, okay? So what it's going to do is at this setup, if I put this in, it will effectively cut the signal in half. So my 50 millivolts should be, when I plug this in, even though there's 50 millivolts coming out of this signal generator, there should only be about 25 millivolts now getting into the scope. Let's see what happens up here. And you can see 24.7. Now, remember, there's a wee little bit of loss in the cables and in the terminator and all these things, so that tiny little portion of a millivolt that you're losing has to do with all of that. And the higher the frequency you go, the more the cables and things will begin to give what's called an insertion loss. By inserting all of this cables and connectors and things, they absorb some of the energy. Now, to go even further, let's say we go to a 20 dB attenuator, and you can see how tiny it is now. Now you're down to 5 millivolts roughly, okay? So by putting that 20 dB attenuator in there, you are reducing the signal level by a factor of 10. So it's 1/10 of that. And the beauty of it is you can stack these attenuators together and add them up. You can see now we're down to 2.7 because we added that 6 dB in there. And again, look, you can look all this up, and I can put a 10 dB on top of that. And you can see how rapidly this becomes a very, very tiny little signal. And the oscilloscope pretty soon is not going to be able to see all the noise we're getting, and that's because the oscilloscope is getting at the end of its range where it can. I'm looking at 1 millivolt per division. Oscilloscopes really aren't designed at looking at radio signals at that low of an amplitude. You really need a spectrum analyzer to do that. But you can see how tiny it is. We're down now to 970 microvolts. And since our signal generator can go down to 1 millivolt, you can see rapidly how we can easily get down into the microvolt range that we need for our radio. And I'll show you what I have down here. And you can see they're just all stacked up, and you can get attenuators with higher dB attenuation, or you can get like 220s and put them in order. And again, the dB thing is another whole video. But between these attenuators and this signal generator, you can use it on your radio. And that's really what this video is about. Now, dealing with the RF and the IF and the AF and all that, that's another whole kettle of fish. But I hope that explains to the person that asked about this how to set up their basic function generator to do modulated signals and to connect to a radio. It can be done. Okay, let's put it all together now. I'm at 600 kilohertz. I'm at 500 millivolts RMS because I'm driving my little antenna loop. Let's go down to that. There's your antenna loop. And the radio is just sitting on top of it, and it's going to radiate the signal up into the internal antenna. And let me get you at a better, where you can see. Seeing is a good thing, isn't it? Alright. There we go. I'll turn the radio on. And I'll put the microphone up by the radio. And let's turn the turn the output on. And you can see we're now picking up the unmodulated carrier. Now let's turn on our AM modulation. And you can see the radio did just what I said. It received the carrier signal. It received the carrier with the modulation. It stripped the modulation off and amplified it and outputted it at the speaker. Okay, let's try something else now. Let's try FM. Okay, I now have the radio set to FM, and it's tuned right about to 90 megahertz. Okay, the dial accuracy needs to be adjusted on this a wee little bit. And if I turn it up, you can hear it's already trying to receive a station outside. But watch what happens when we turn on the unmodulated FM carrier. And you can see it goes dead silent because now it's locked on to that 90 megahertz signal coming out of the little antenna. Now what happens if we turn on our AM modulation like we did with the FM radio? You can just barely, if I turn off the fan off of my oscilloscope, can you kind of hear it? It's very, very quiet though. And there's a reason for that. It's because FM radios are designed to reject AM, and this is a super, super strong station, so a wee little bit of the AM is bleeding through. But watch what happens if I change the type to FM. And I go to modulation frequency, and I go to 400 hertz. Wow! That's pretty loud, isn't it? And let's move the deviation down to, let's say, 1 kilohertz. It got real quiet, didn't it? And if I go to 10 kilohertz, you hear it? It's really quiet. If I go to 50 kilohertz, And if I go to 100 kilohertz, it's going to be crazy now. Okay? And there you have it. Now I know this is just scratching the surface of all this, but I wanted to kind of explain a few things that I was trying to go back and forth with a viewer on some emails, how this stuff works. And he had asked some specific questions. That's why this video is the way it is. So there's a lot of you who are asking 1,000 other questions, I'm sure, right now in your own minds that we didn't cover. But I hope this at least gives you a rough idea for those of you who don't work with radio and want to, or that have some test equipment and is just getting into radio and you just can't quite figure out what this test equipment is all about. Now, of course, some other things is how to connect the test equipment to the radio and how to measure it and things like that, and what an intermediate frequency is. All those things, but those are things that come along later. This is the basics of what happens inside a radio and how a radio signal is put together. So I hope that helps you out, and until next time, I wish you all peace, joy, happiness, and good health, and maybe we'll do some more videos like this in the future. We'll see. Take care, everyone. Bye-bye.